Hello and welcome to week 6 in Statistics for Psychology, taking on 2 chapters of descriptive statistics. One is central tendency, the middleness of things, and the other one is variability, the diversity of things. So when we look at data and we're describing it, we want to know the middleness and we want to know the variability, the diversity of our data, and that is two of the very most important ways in which we describe data. So we started off chapter 5, central tendency. And the middleness of something really depends on the type of data that we're looking at. So we look at this chart here in the course book and we have nominal data, ordinal data, interval data, and ratio data. And each one of these has characteristics that determine what particular tool will we use for measuring the middleness of things. And on the next page, there's a chart very similar to the chart that is the decision chart on what statistical tools you will use when you're looking at hypothesis testing. This one looks at descriptive statistics. So you'll see over here on the left that descriptive statistics, central tendency, what is the typical score? If your data is nominal, you would use the mode, which is the most, it's defined as the most common score. In ordinal scales, you would use the median, what's in the middle. If you lined them all up from smallest to biggest, what's the one in the middle? Now, when we look at interval and ratio scales, those we can ask what is the middle, the median, but we can also use math and compute the arithmetic mean, which is really the average. Okay, so back to that chart here, we have nominal data has the mode, ordinal data, the median, and then interval and ratio scales have both the median and the mean. The decision to do either one of those really has to do with the skew of the chart. Because if you have, for example, if we looked at income, we're going to look at the difference here about when we would use median versus mean on ratio data. Our top tier ratio scales, 0 point, and equal numbers. So let's look at income. So let's say I'm in class teaching statistics, and lo and behold, Taylor Swift got tired of touring around and decided she was going to come to KVCC and major in psychology. For one, I'd be thrilled. That'd be awesome for that to happen. But here's Taylor sitting in my statistics class, and we're going to do a little study on income. Okay? Now, so I use a private survey so everybody can put in their income. So there's 15 of you all sitting there and everybody's putting their income. Taylor puts in her income. And guess what? Taylor's income is a little bit more than yours. I can probably safely say that. In fact, it's a lot more than that. In fact, if I take into consideration Taylor's income, and let's just say she makes $100 million a year, and I use the arithmetic mean, I average, I would get an average of my class at around $50 million a year. Be the average, we take into consideration the outlier of Taylor's income, it would push the average way over. It's just skewing away. And this puts a negative skew. Remember the tail points. It's a negative skew of the data with Taylor's income throwing off the average by almost $50 million. Everybody else is bundled around the bottom. Mean doesn't work when you have outliers like that. It throws off the whole usefulness of the middleness. Is that really the middle? Is that really the typical score? No. That's when we would want the median. The median is just the one in the middle. If you line them up from smallest to biggest, it's just the one in the middle. So it'd be student number 12 or whatever. Not that. Let's say there's 15. Taylor on the top end. It'd be student number 7 in terms of increasing income. Let's say it's $32,000 a year. Okay, that'd be the middleness. It keeps us from getting the middleness thrown off by Taylor's income. So there's decision making that goes into what is the best way to describe this data. In fact, oftentimes when we're reporting ratio data, we will report all of these. There can be a most common score. Not as useful when you're looking at something like income because income varies incrementally, but there could be a common score. There's obviously a median and there's obviously an arithmetic average. So when you do the descriptive statistics tool in Excel, gives you all three. And if there is no mode, it just puts error. There's no, like, and in lots of data, when you're looking at 3.67 as a data point or something like that, what's the likelihood that there's going to be more than one 3.67? Pretty low. You'll get you get sometimes no identical scores. So therefore, there's no mode or modes, plural, certainly multimodal data. So let me catch up here. So mean, median, mode, you see the descriptive statistics in there. The discussion for this particular chapter, you go in the media. This is the web, the websites, Google, whatever. Find a news article that uses central tendency, that mode, median, and mean. And tell me why they picked the one that they did. If they reported all three, why? If they reported median, remember that's how you deal with outliers, why? If they produced mode, what are they looking at? Notice how the types of data are important in making the decision as to which central tendency tool you're going to be using. The quiz asks you to look at the medal count. Now the U.S. medal count, and do some statistics on that. That is actually on page 106 here. It's hidden a little bit. On 106, I wanted to point this out. If you look on the left side here, this is the Tokyo Olympics 2021. I promise I'll update this to the Paris Olympics or maybe even another one. 39 golds, 41 silver, and 33 bronze. Okay? And we're going to be using, we're going to take, this is actually nominal data, and we're going to mess with it by calling gold 1, silver 2, and bronze 3, and then we can do statistics on that. Naughty, but we're going to do it anyway. And then I ask you some questions about that. Ask you some questions as to what can we gather from that information. And finally, I'm asking you to do descriptive statistics. That's the simple tool within Excel. But what I'm having you do this on is an extremely large data set where you can't count. You will not be able to go through this thing and count. I believe there are thousands of data points. That is nothing to Excel. It's no problem. You're looking at a huge database of information on happiness, and it's the happiness survey, and I want you to calculate the descriptive statistics and then report out on that. Tell me what those descriptive statistics say about happiness. I picked a large existing database so that you can understand that large databases should not intimidate you. They're easy to work with. They're fine when you have a tool like Excel. And that large database is actually, let's look at this here. It's in the assignment. Right here, here's the assignment. This is the data. This is the general survey that it came from, if you want to look into that. This right here is an Excel file. This is that Chapter 5 assignment data. You need to download that document, put your title page in it, there's your data, and then your computation from the descriptive statistics, and then a text box explaining what you learned looking at the descriptive statistics. But that's where the data is. I'm giving you the data in the form of an Excel document. So download that document and then work with that, add the pieces, and then upload it to the Dropbox. That puts us into the next chapter, looking at, so there's middleness and now there's diversity. Diversity, or how things vary. So we're introduced here to range, interquartile range, standard deviations, how we calculate the standard deviation, percentiles, all of that stuff. So I have some notes here of some things I wanted to look at. So first, the calculating of the standard deviation, explaining what that is when you look at the word standard deviation, standard would be average, norm, deviation. So if you look at all the data points and you measure the distance between the data point and the mean, this is for ratio data only. The distance between the data point and the mean, and it doesn't matter which direction. Even though you might have one data point on the negative side, it's lower than the mean, and one that's higher than the mean, doesn't matter. It's just the distance is how far is the data point from the mean, and we take all of those numbers, how far, and we average those. That's standard deviation. So it's the average deviation from the mean is what standard deviation works for. And this is how we calculate it. Look at that. The square root, and we have the denominator, the sum of the data point, all the data points minus the mean squared. The squaring makes it a positive number, because we always want that all to be positive. Because if take the difference, take that x minus the mean, it might be negative. So we get that amount, but then we square it. But we're going to see that we're going to square root the whole thing and take out the square. So those cancel each other out in the end. But then we divide that by the number of data points in our total distribution, -1. And I'll be getting to that -1 later in the course. This is your degrees of freedom. It has to do with sample size and how many variables that you're looking at. And I'll explain degrees of freedom at another time. But this is how you get the standard deviation. You take each score minus the mean, square, add those all up, and divide by the number of scores that you have. It's actually a very simple equation, even though it kind of looks a little intimidating there when you have like the sum sign and all that stuff. So continue here and make sure we have... Now, when we're looking at the normal curve, let's see, get on the right page here. When I introduced the normal curve, we had these numbers on here. Now, this particular example is the IQ normal curve, but in every normal distribution, and remember when we're talking about normal distributions, we're talking about the distribution of sample means. We're not talking about raw data. We're talking about the distribution of sample means, which mathematically, theoretically approach the normal curve. What we will find is that particular percentages lie underneath the curve based on lines of standard deviation. So when you look at this one, okay, the 100 is the mean, 115 is the score, this right here, that's one standard deviation above the mean. This is 2 standard deviations above the mean. This is 3 standard deviations above the mean. 1 below, 2 below, 3 below. And the number of scores that you have, regardless of the scale here, regardless of what these numbers are right here, in a normal distribution, 34.1% of all the data lies between the mean, and a +1 standard deviation. That's a rule. That's always. And look at it, a normal curve, we know that 34.1% of all the scores lies between the mean and the first standard deviation. If you look back at this, we'd say, well, how many scores lie between the mean and the second deviation? We would add 34.1 to 13.6, and we would get the percentage of people, of sample means, that lie between the mean and +2 standard deviations. So you just use, this is just simple addition to determine how much of the population lies under certain components. So those lines that are in all of the examples of the normal curve are lines that delineate standard deviation. Now, in this particular example, we're looking at IQ. IQ scores are methodically created in order to give you a normal distribution. And so in IQ scores based on an average of 100, no matter what, if everybody suddenly became more intelligent, we would all still have an average IQ of 100. Just mathematically, that's the way it works. And each standard deviation is 15. So 15 is the standard deviation of the normal curve that describes the distribution of sample means of people who have taken an IQ test. It's all been done for you. You don't have to understand it any more than that. But now we will see that those percentages represent the likelihood that your sample is going to fall there. So there is a 34.1% likelihood that your sample mean, just randomly, is going to fall between 100 and 115, or 1 standard deviation above the mean. There is I'll add it here, there's a 68.2% chance that your sample mean is going to fall between plus or minus 1 standard deviation. There is a incredibly unlikely chance that your sample mean is going to fall more than 3 standard deviations above or below the mean. In fact, you'll see the 0.1% chance. Very, very, very unlikely. This is so vital. You're going to see this being so vital. Okay, looking at different, that's going to be vital in this way. I've taken this same chart and I've added what we call the 5% and 1% criteria for testing hypotheses. And it's essentially this. If I've taken a sample of people and I'm looking at a score on something to which we have norms, we have the data as to where people would normally score on them. So I take my sample and I want to prove that I want to have evidence that my sample is different than all the other samples that I could have had. That sample has to be so different that my mean on my sample lies beyond these points here, either the 5% criteria or the 1% criteria. 5% is easier to get to. It has to be different than 95%. The 1% has to be different than 99% of the possibilities. It has a 5% or lower likelihood of happening by chance, or a 1% or lower chance of happening by chance. And the same thing applies on the other end, just going in the other, a 5% chance that is that low or a 1% chance that it's that low. These are the lines in the sand that the field of psychology has said these are significantly different scores. So if I have my sample and I think they're really smart, significantly more smart, I can look, the statistical significance would be based on, does the mean of that group, the mean of the group, is it higher than either 95% or 99% of the other people who have taken that test? When we are doing hypothesis testing, we are introducing interventions, we're comparing groups, we're looking at how things change over time. We're taking those and we say, is my group significantly different from what I would normally expect to get if I was sampling everybody? And if my mean is more different than 95% or more different than 1% on either direction, then I have statistical significance based on this. So that's an important aspect to understanding this. Now, when we look at variability, one of those is look at the standard deviation. I want to show you one more graph here. High standard deviation means a lot of variability, a relatively flat curve. There's lots of different distributions everywhere. A very low standard deviation would be a very thin curve. So we see in this here, we have a standard deviation of 5 would be the blue line, very small. Then a standard deviation of 10, it's a little bit lower. And then look at the standard deviation of 20. There's lots of scores. So remember, that's the average distance between any data point and the mean. So if that's a big average, that means they're all over the place. If it's just if the standard deviation is very narrow, we have not a lot of variance. This is where we get the concept of homogeneity. Woo, pulled that on the first effort. Awesome. Homogeneity is a word that we describe when we're looking at samples as to whether they're all very similar to each other, very low standard deviation, or whether very diverse. So non-homogeneous, homogeneous, non-homogeneous. And that term relates to social psychology when we're talking about groups. Is the group all very similar? It's a homogeneous group. Or is the group very diverse, a non-homogenized group? Now, we do know that there are some advantages to groups working together to be homogeneous or non-homogeneous, and that's the first discussion. We take that idea of variability and apply it to social psychology and think, if I'm putting a group of people together to solve a very complex problem, do I want a homogeneous group or do I want a non-homogeneous group? What do you think? What's been your experience? And there are advantages to both. So, consider two things: the quality of the solution and the speed at which we get to the solution. Two factors that we can bring into that consideration of the homogeneity of groups that are engaged in problem solving. And finally, the assignment, I'm having you look at a whole bunch of different calculations of variance and the variance statistics that we get from descriptive statistics. That one tool also gives us a number of factors that relate to variance. We're looking at the heart rate as a measure of stress. That's the operational definition of the psychological concept of stress. It's not the only one, but we're going to look at heart rate. That's like someone's current stress. We're going to measure it. Got all those numbers. Give me the variability in that, and then you're also going to give me the descriptive statistics. Now, because of the way Excel works, Excel, I believe, defaults to sample. There is a slight difference. If you're doing statistics and you actually have the whole population, and that's possible. If I was doing this study on stress, all the people that have ever been on the moon, I can get them all. Well, not all of them. Some of them are not around anymore. But let's say they're all alive. There's only a few people. So technically speaking, I could look at the entire population. I could look at the entire population of living presidents of the United States. I could look at the entire population of faculty at KVCC, if that's how I'm defining my population. So Excel allows for some variability in the results of our statistics based on whether we are assuming that we have captured the entire population or whether we're attaching a sample. There should be more variability somewhere. That's a factoid to consider when you're looking at each one of those. So make an observation about when you're doing statistics on variability based on population versus sample, which one, population or sample, tends to calculate higher variability. I know. Just follow the instructions in the you'll get this. It's a lot of words throwing at you. You will understand this. This is the first step into taking a deeper dive into descriptive statistics. So here we have variability and central tendency. Have a great week. Look forward to the discussions and these assignments. Take care.